Good day, and welcome to the Grade 12 Physical Sciences. My name is Nonkululeko Madondo, and I am your Grade 12 Physical Sciences teacher. Today, as you guys know, in this new program, this is the Africa Teen Geeks STEM Digital School, and we are starting over. We're doing some good revision for all of you in order for you guys to prepare yourselves for your prelims that are upcoming. Before we get started, I just want to remind you guys that we work from mostly the textbooks that I'm using in this classroom. I'm using the Siavula textbook, and I also use the Study and Master textbook. So if you have any of those textbooks, then it might be easier to follow through. But any other CAPS-approved textbooks works well in this class. So we're starting from the top, which is kinematics, and we're going to be doing momentum and impulse. What we're going to be doing today, basically, we're going to be just revising. So everything is going to be summed up into one lesson, and we're going to go through and do some exam questions and see how we need to answer these questions whenever they come to pass. So thank you, guys. Please make sure if you do need some external material, you can get it on Snaplify. And Snaplify is an application you can get on Google where you can get all your textbooks, not just for physical sciences, but for your other subjects too. So if you do get a chance to do that, make sure that you use the opportunity. It's absolutely free until the 31st of December 2020. And I think it's something that anyone should take advantage of. Okay. So the content of this lesson, basically what we're going to be doing revision on, we're going to be doing momentum, we're going to be doing collision, and we're going to be doing impulse, because that's basically this chapter that we're going to do with it. Like I mentioned, we're starting from the top. So which means that next week, you guys can also revise the next chapter that comes after this, okay? So these are the three things that we're going to be learning about today. So what is momentum? Now, I want us first to look at a practical example. Why are we doing this, guys? I just want to give you guys an idea on how to imagine what momentum is. So let's look at a practical example. We have two balls moving on a smooth surface. One ball is big and the other one is small. So which ball would be much easier to stop? Okay? So basically, this takes us to the detection of the combination of mass, velocity, and velocity, which determines the quantity of motion of an object. So basically, as you can look here, this is a small ball that we have, it's 2 kilograms, and this is the big ball that we have here, which is 10 kilograms. So which one will be easier to stop? It's obviously going to be the smaller ball. That one is going to be easier to stop. Why? Because it's much lighter. So what counts here basically is the velocity and the mass. Those both account for the speed or the motion that the ball will reach, okay? So at constant velocity, it means that they are moving at the same velocity, but it would give us a different answer if, for example, they said they're moving at different speeds. Then that would have given us something that we need to calculate. But if they're at the same speed, this one will likely be the one that stopped faster. So the quantity of motion can be increased by increasing the following. So if we wanted to increase the quantity of the motion, the one thing that we can increase the mass of the object. Number two, we can increase the velocity of the object, or we can increase both of them, which is the mass and velocity. What this basically means is that as these two balls, we mentioned that this one could be stopped much faster. But if we increase this one to be the same mass as the 10 kilogram ball, it means that they would both be stopped at the same time. Or if we decrease this speed and increase this one, then this one would still be the one that gets stops faster. But if we increase the speed of this velocity, even though it's 10 kilograms and this is 2 kilograms, if this speed here increases, then this one could likely be stopped much faster. So it always depends on what you change. You can either change the mass You can change the velocity, or you can change both the mass and the velocity. So what is this? This quantity of motion is what we call momentum. So whenever we're working with momentum, this is what we are calculating. Calculating the quantity of its motion. Okay. So what is our definition of momentum? It says here that the momentum of an object is the product of the mass of the object and its velocity. Okay. It's the of an object is the product of the mass and the velocity. As we've already mentioned from our previous example, that the mass plays a role and the velocity plays a role. As you guys can see here, it's what determines the quantity of the motion. So once you have your velocity and you have your mass, then you can calculate your momentum. Okay. So momentum is a vector, so which means that it has both direction and magnitude. And please guys, do not forget this part of the direction. Why do we need direction? Because if something is in motion, there's a certain movement or a certain direction that it's taking, or displacement. So that's why it's important that when we work with momentum, you are able to elaborate that you're moving 2 kilograms per meter second -1 on your right or on your left or to the top. Those things are also things that are going to be counting marks for you. So those are things that you're going to have to know. Okay. So it says here, momentum is calculated using the following equation. So this is our equation for momentum. Okay, this is a P, okay? I don't know, it just looks very funny, but it's a P. So we use a small p because the capital letter P is for power, and we are not working with power at the moment. We're just working with momentum. So the small p is for momentum, and that's going to be in kilograms meters per second, because this is a product. As you can see, this SI unit already, it tells you that it's a product of mass, which is in kilogram, and velocity, which is in meters per second -1. Okay, so that is going to be equals to the mass, which is measured in kilogram, times the velocity, which is in meters per second. Okay, so when an object changes its velocity, then it will experience a change in momentum. So now we're taking it a bit further. So now we first focus on the definition of momentum, but sometimes we get to experience a change in momentum, and that happens when an object changes its velocity. So there's certain conditions within the system or whichever object that you're calculating that can allow its velocity to change, and it change in a way where it either increases its velocity, or it slows down its velocity, or it stops the motion completely. So that is something that happens. That brings us to calculating the change in momentum. So those are conditions that are also part of momentum. So if the object changes direction when changing velocity, it will experience a much greater change in momentum than if its direction doesn't change. Okay, so which means that if you're working with opposites, okay, we're going to get to the definition of that as we move along. I'll explain it more when we get to it. Here we have it. Okay, so it says collision of particles or objects occur when they come in contact. Sorry about this error. Contact with other particles or objects. This results in change in velocity, so their momentum results in a change as well. So this is our equation for our change in velocity. Our change in velocity is going to be equals to the change in velocity, the final change in velocity minus the initial change in the final momentum minus the initial momentum. So that will give us the change in momentum. Okay, I'm going to explain to you guys just now what it means. So let's start with the change in momentum for a single object by breaking down in the following cases. Okay, so this one, the final momentum, it means that the one after the change in velocity, and the one for initial momentum is the one, the start. For example, if you're going to throw a ball, the velocity that you use to throw the ball, that's your initial momentum. But if anything, or there's other forces that influence the change in your velocity, after that, that's going to be our final momentum. Okay, so let's focus on the cases that we're going to be working with regards to the momentum and change in momentum. So we're going to start with the first case. It says here, a ball bouncing off a wall. So you can have if we have an example whereby we have a ball bouncing on the wall, you can see it here. Here's the ball, it's approaching the wall, and then it bounces back. So which means that now we have two momentums. Why? Because we've got two velocities. We've got the velocities where the ball is approaching the wall, and then we have the velocity of the ball bouncing back from the wall. Okay. So in this case, the mass stays the same, but the velocity changes. Okay. So here we've got a constant mass. The mass is the same because it's still the same ball, but the velocity changes because after it has an impact here, the velocity that's moving away from the wall will be different. So this is going to be our change in momentum is equals to the final momentum, which is this one here, minus the initial momentum, which is this one there. Okay, so we're looking for this piece over here. Okay. So now we're going to have the second case, which is case 2. This is where an object that is going to stop. Remember, now we spoke about an object that bounces back, and now we come back to an object that literally stops. An example is a ball that gets caught in a net. For example, when you throw a ball and it's caught in the net, it's going to stop. It's not going to go further. So it's going to stop. So which means in this case, your final momentum is going to be 0. Why is your final momentum 0? Because your velocity is going to be 0. When anything that is moving stops, your velocity becomes 0 because velocity has to do with motion and movement. So if there's no movement, then your velocity becomes 0. So here we have it. Now this is, in this case, will be our net. So this is our ball bouncing, going to the net, but only to find that it's not bouncing back. It just stops and drops down. So our final momentum is going to be 0. So in this case, our change in momentum is going to be equals to the final momentum minus the initial momentum. Okay. I hope that everybody is understanding the concept of momentum as we're coming through. And now we're going to move to our third case. Our third case is when an object continues more slower. Okay. So what this means basically, it means that I can give you guys an example. An example of an object that continues more slower. For example, when you throw a ball and it hits a window, after it hits the window, the speed of the ball after it hits the window is going to be much slower than because of the impact that it had on the window. So it's going to be much slower than the momentum that it had in the beginning. So which means that the velocity is also going to be much less. Okay. So an example is when a ball hits a window and it goes through, but at a slower rate. Please do note that even though the momentum is in the same direction, the change will be less due to the direction in the opposite motion. What does this mean, guys? It means that when we have change in momentum, remember we mentioned before that even if it increases when they're in opposite direction, but it decreases when they're in the same direction. So when you look at this triangle P of momentum is equals to final momentum minus initial moment. What you should notice there is that we have a negative sign there. Here's our negative sign. So if these two are in opposite direction, the signs are gonna add together. Okay. Because if your final is a minus and your initial is a negative, they're going to give you a much larger value in the direction of your initial velocity. Okay. But if your momentum doesn't change and it's moving in the same direction, okay, it does change, but it's moving in the same direction, then it's going to be less because your signs are going to be opposite. So which means that your minus, for example, if you have your final velocity as 5 and your initial velocity as 2, it's going to minus. So it's going to be minus 3. Okay. So that's what it means when it says that when they move in the same direction, your change in momentum becomes less. But if they move in opposite directions, then your change in momentum becomes more. Okay. So now we move on to the fourth case. The fourth case says that when an object gets a boost, okay? This happens when a ball gets in contact with something that increases its velocity. An example of this is when, for example, you are playing squash. When you're playing squash, you're gonna realize that usually there's a ball that's coming through, but you're going to hit it with your racket to the same direction. Okay. So you are what are you doing there? You are increasing its speed. Okay. So what are we gonna have there? So here we have it. This is the first person holding a racket. They put the ball there, but when it gets here, you see the tennis ball and you hit it further to have more momentum to go further. So that is also something that can happen. It's a change in momentum, but in this case, it will be also, you see, because they're in the same direction, this is going to be your change in momentum. Okay. I hope that everybody understands these cases because, they come in different ways, but you need to know what case your question involves. Okay. So, before we get to this one, oh, but it's fine, you can go through it. But I just want us to go quickly to a textbook. This is the Study and Master textbook. I just want us to have a small example of momentum. So it says here a 5-kilogram block is moving in a straight line at 2 meters per second towards the left. Determine the momentum of the block. So what do you have there? You have mass and you've got velocity. So which means that you can calculate it because it's a straightforward question. But remember, guys, they can ask you for anything. They can ask you for mass, they can ask you for velocity, or they can ask you for momentum, depending on what is given. And guys, another thing that you guys also have to note is that sometimes you find that they give you your block in grams. Okay, so if they give you in grams, then you have to convert it to the standard unit, okay, to the SI unit. So it will have to be 5,000 kilogram. Okay, it's gonna be, if this was gram, then it would be 0.005 kilogram. Okay, so you always convert it to your SI unit before you do anything. Okay, so here's another example. So an athlete with a mass of 60 kilogram and a constant momentum of 96 kilogram meters per second in an easterly direction. Okay, you see why this is momentum. So they mention the direction. So you must always make sure you mention it as well. And even velocity, remember velocity is also a vector. It also has direction. That's why they mentioned 2 meters per second towards the left. Okay, so always pay attention to that. Even in your answers, it needs to be like that. So they say determine the velocity of the athlete. So we already have our momentum and we've got our mass. What are we calculating? We're calculating the velocity. So you can do your substitution, and it means that you're going to say 96 divided by 6, and that's going to give you 1.6 meters per second. So when you write your final answer, you need to write a proper code according to your direction. If this direction to your right is positive and this one to your left, if you're going to have a negative answer going that way, then you're going to say towards west or towards east. Okay, so you need to always mention that. After you find your answer, then you're going to say the velocity of the athlete is 1.6 meters per second in an easterly direction. Okay, I hope that all of that makes sense. Now let's move on to the example of the change in momentum. Okay, remember what case is going to be this one. This is an example of the first case that we spoke about. Why is this case one? Because you've got a ball that's bouncing on a wall. So this could be a ball, could be a tennis ball, it could be a golf ball, it could be anything, but it's bouncing off this wall. So we've got our initial velocity that's going towards the wall, but it bounces back, and now we've got our final velocity of the ball that's coming back. So what are they saying here? They say a tennis ball of a mass of 56 grams is thrown towards a wall and hits the wall at 45 meters per second. The ball bounces off the wall with a velocity of 40 meters per second as shown on the guys. I've got a little bit of grammar errors here. So they say calculate the change in momentum of the ball. So what do we do first when we have a problem of this nature? If you're not given a graph or a diagram, you need to be able to start drawing that diagram of what you're going to use. Okay? And then number two, you need to show the directions. You need to have your direction. Which direction is positive? Are you going to choose this one as positive or this one as negative? Either way, you will get the correct answer as long as you know how to apply them. Okay? And then the change in momentum. Now we need to know which formula we are going to be using for the change in momentum. So the solution, like I mentioned before, if there's no diagram given, you can draw yourself a diagram to help you understand the question. And it's always better when it's written down. So write all the given information and choose a positive direction. Don't forget to convert the units to SI unit. Okay. Why are we converting in this case? Because our mass was given as 56 grams, but we know that our SI unit is in kilogram. So we need to change the 56 gram to kilogram, and that's going to be 0.056 kilogram. Okay, so now that we have placed everything that is given and we've chosen right as positive, we can now go and plug into our equation. So here is our equation right here. Our equation is going to be the change in momentum is going to be equals to the mass times the change in velocity. So do you guys notice something that's happening here? Whenever we work with change in momentum, the mass stays the same, but the velocities are the ones that change. Okay, so you're going to have your initial velocity, and you're going to have a final velocity, but your mass will be more or less the same because you're speaking about one object. Okay, that is acting. It can act on another object, but we're focusing on the object that is in motion. Okay, so I don't know if we can go and see another example on the Study and Master textbook. There we have it. So here we've got another example. It says here, a car with a mass of 600 kilograms travels in an easterly direction along a straight horizontal road at a constant velocity of 20 meters per second. So the driver suddenly increases his velocity to a constant velocity of 24 meters per second and continues to drive in the original direction. Okay, so which case are we working with here? I think it's a case where we talk about continues at either a slower or a faster rate. So it's the same speed, but it does not stop and it doesn't turn back. It continues, but in a change in velocity. So what they want to know here is for you to determine the change in momentum of the car, and number two, to draw the vector diagram to illustrate the relationship between the initial momentum, the final momentum, and the change in momentum of the car. Okay, so now we're going to take the easterly direction as positive. So it's always best, the given direction is the one that we always take as positive. So it's going to be change in momentum initial is going to give us as 12,000, and change in momentum final is going to be 14,400. So why we're able to look for all of these because we've got the mass. It's still the same mass because it's still the same car. The only thing that has changed is the velocity. So our change in momentum is going to be equals to momentum, the final momentum minus the initial momentum, and that's going to be 14,400 minus 12,000, and that's going to give us a positive 2,400. Remember what we spoke about, guys, that when they're moving in the same direction, the change in momentum becomes less. But if this was, imagine if they were in the same direction and this was either negative or this was either negative, it was going to be an increasing value. It's going to be a very high value because it was going to add these two momentums together and we would have a high momentum. So you should also take note of that. So the change in momentum of the car is 2,400 kilogram meters per second in an easterly direction because it's positive. Remember, we mentioned that the easterly direction is the positive direction. Okay, so now we're going to have our diagram that illustrates basically the whole problem. So this is our initial momentum, and this is our final momentum, and that will be our change in momentum. Remember, the change is the one between the initial and the final. So that's why you can see here it's a connection between the initial and the final. Okay, I hope you guys are remembering all of this as you guys have done it throughout the year. So now we're going to move on. We've spoken about the momentum. We've spoken about the change in momentum. Now we move on to the rate of change in momentum. Guys, please make sure do not ever mix the two up because they are very different. Why are they different? When we speak about rate, there's always got to do with time. So it's got to do with reference to time. So which means that now, before we had the change in momentum, but it didn't matter how long it took or how much distance it was. But in this case, with respect to time. So for an object to change velocity or change direction, a net force needs to be applied to the object. Okay, so for an object to change velocity, a net force needs to be applied to the object. What does that mean, guys? Remember what I spoke to you guys about, that in a, for example, when we have a ball, like I mentioned, when you're playing squash and someone hits the ball, but then they hit it further, that is a change in velocity with respect to the net force that was applied on the object that is in motion. So we're going to have our net force, okay, which will be equals to change in momentum divided by the change in time. So the net force is going to be the net force measured in Newton, okay? And then the change in momentum is going to be the change in momentum measured in kilogram meters per second. So we know this net force it's either going to be given or it's either going to be required for us to calculate. The change in P is obviously the final momentum minus the initial momentum, and that's going to give you your triangle P. You can always either calculate it separately or calculate it within your calculation. And then now we're going to have the time. So the time, it's obviously the time that it takes for your, for example, if they said that you threw a ball on a wall and it came back after 5 seconds, it means that the change in time will be 5 seconds because it's the time it took between going and coming back. The initial time minus the final time minus the initial time. Okay. So now we're moving on. It says the rate of change in momentum can be expressed in Newton's second law of motion. Okay, remember we've spoken about Newton's second law of motion back then in grade 11, but now we're going to be taking it further with regards to your grade 12, with regards to your momentum. It says here on Newton's second law of motion, the net or resultant force acting on an object is equal to the rate of change of momentum. Okay, so what does that mean? It means that your net force is your total force basically, okay? So net force is your total force acting on an object is equal to the rate of change of momentum. Okay. Does it make sense? I hope it makes sense because you've got your momentum, you've got your total momentum, and you've got your time it took. So that will be your change in time. Okay. So this is what the Newton's law of motion states. So basically, the net force is proportional to your change in momentum, but indirectly proportional to your change in time. Okay. So if you increase the time, the longer it takes, the less your net force becomes. Okay. I hope that it makes sense. So now let's go to an example of rate of change of momentum. So it says here a remote controller toy rocket. Okay, so this is our little toy. It's a rocket with a mass of 0.5 kilograms. So the mass of this whole rocket is 0.5 kilogram. Is launched so that it reaches a velocity of 35 meters per second in 2 seconds. Calculate the net force acting on the rocket. Okay. So they say it's done so that it reaches a velocity of 35. So here in this case, our initial velocity is going to be 0. Why is our initial velocity 0? It's 0 because in the beginning when it starts, it's standing still. But then it rockets up to 35 meters per second. Okay? So our change in time is going to be 0.2 seconds, and our mass is the one that is given here. So it says here, calculate the net force acting on the rocket. Okay, so basically here it's self-given because you just plug everything into your equation. Okay, but I'm just reminding you guys, please do not confuse the rate of change of momentum with the change of momentum. The change of momentum is different from the rate of change. As you can see, the change of momentum is already incorporated in this equation. It's this part over here. So make sure you do not get confused, grade 12s, and end up writing the wrong answers. So here's our solution. Like I told you guys before, if you do not have something of this nature, you can even write here, V initial is 0 and V final must be 35 meters per second. And the time in between will be 0.2 seconds. So now after you adjust your sketch, you can even write on your answer book where you have it, okay? And then you're gonna write what is given. What are we given? We're given the mass, we're given the velocities, and we're given the time, okay? So anything that starts from rest starts from 0. So the F net is gonna be change in momentum divided by change in time. So change in momentum, we know that it's both the same mass because it's one rocket. So we're talking about an object in motion, a single object in motion. So the mass stays the same. So it's going to be the velocity, final velocity minus the initial velocity divided by the change in time. And this is what it's going to give us. It's going to give us 0.5 times 35 minus 0 because our initial velocity is 0 divided by 0.2. So let's not forget, we need to choose, I forgot to mention this, don't forget to choose which part is positive. So in this case, if we said the motion going up is positive and you get a positive answer, it means that it's going to be 87.5 newtons up. Why? Because up is in a positive direction and we got a positive answer. Okay. I hope that all of this makes sense. Then we move on. We move on to Newton's second law of motion. It says if a force is acting on an object whose mass is not changing, Newton's second law describes a relationship between the motion of an object and the net force on the object through this equation. Okay, so this is an equation that you've been working with. It says the net force is equals to mass times acceleration, the net acceleration and the net force. Okay, so now if we're going to go and plug it in this equation to try and prove, basically here you are proving that force net is equals to the rate of change of momentum. Basically, that's what you're proving, okay? So we're going to start here. Force net is equals to mass times acceleration. And we know that for acceleration is equals to change in velocity divided by the change in time. And the mass stays the same. Okay? And then from there, it's going to be the mass. Then now you can multiply together. It's going to be mass times change in velocity divided by change in time. So therefore, now we know that this is equals to momentum. Mass times the change in velocity is equals to the change in time. Okay. So if you have an object like this, you're going to have your little box. It doesn't change. It's still on the same mass, but it's moved to a certain position. In this position, you need to apply a force for this object to move. So when we calculate the force net and we calculate the rate of change, there's a specific time that you're going to take in order to reach to position B. So this is position A, or the initial position, and this is the final position. So from initial position to final position, there's going to be a change in time. Okay, so that's what this is defining, that you have the same force applied, but your momentum is going to be different because of the change in time. Okay. So now we're moving on. So we've spoken about momentum, the change in momentum, the rate of change in momentum. So now we come to the part that talks about the collisions. Okay. So what does the law of conservation of momentum say? It says the total linear momentum of an isolated system remains constant, or remains conserved. So what this means is that when two objects collide with each other, their momentum changes. Okay. I think I just want to show you guys an example of particles that are colliding together. Okay, I'm just looking for an example of a collision theory. Okay, so there we have it. So this is an object that two objects that are colliding. So colliding means that they hit each other in simple terms. Okay, so when two objects collide with one another, their momentum changes. Why? Because the velocity that required them to hit each other will be different from the velocity it requires them to split apart. Okay, so that's what it means, that the momentum of two objects that are colliding will be different, will change after collision. Okay, so it can either be more or less, we don't know, depending on the type of collision and the type of particles that collided together. Okay, so that's what it means there. So it says external forces are forces such as friction or brakes on a car. Okay, so now basically the total momentum of the system will not change if there is no external forces acting on it. So when two objects collide with each other, their momentum changes, but the total momentum of the system will not change if there are no external forces acting on the object. Okay, so external forces are forces such as friction or brakes in your car. Basically, it's anything that acts upon the applied motion or applied force. That becomes your external forces, or your gravitational force. Those are all external forces. So a system is a physical configuration of particles or objects that we study. So in problems that we've been solving, we are treating our system as being isolated from the environment. Okay, because once we focus on the on 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 the external environment, then there's going to be forces that are there, okay? Like the air, the wind, or anything that can deter us from calculating the isolated mechanism or object that we are trying to calculate. So the environment is completely ignored in the condition that we use for calculation. An isolated system is a physical configuration of objects that is not subject to any force whose source is external to the system. Okay, so there we have it, a small little sketch. This is our isolated system, and this is our environment. Okay, so it's just like throwing a ball. If this was our ball, if this was our ball, we are ignoring the air resistance. These are all environmental conditions that could be applied to this ball that is moving or in motion towards a destination. So what we do, we just ignore it and we make it an isolated system. So now we move on to the principle of conservation of linear momentum. It says here, the principle of conservation of linear momentum states that the total linear momentum of an isolated system remains constant, okay? So it says of a linear momentum, total linear momentum of an isolated system remains constant. So what does that mean, guys? It means that the initial momentum is equals to the final momentum. Basically, that's what it means. Momentum before is equals to momentum after. So that's what basically a linear momentum states, and what it means when it says it remains constant. It means that they are equal. Or when you add your initial momentum, your initial change in momentum plus your final change in momentum, that is going to give you a 0 because they are equal. The initial part is equals to the final change in momentum. So it's all about the change in momentum. Okay. As you can see here, this alone, PFA minus PIA, it means that the final momentum minus the initial momentum. So basically, this is the change in P final plus the change in E before. Okay, will give us 0. So these are two systems together. Okay, so this is object 1 and this is object 2. We're still basically here dealing with objects that are in collision. So this is these two. So when they come together, they become 1 and they become 0. Okay. So we can also split it again and make sure we've got the before collision part and the after collision part, which is what we do here when you break it down. Okay. So here we just factored out the initial ones together, which is these ones. And then basically we took them to the other side. And we also have our final ones on the one side for both objects. Okay. So P total before collision is equals to P total after collision. So there we have it. Here we did before and after. And in this case, we can also use 1 and 2, object 1 and object 2. So this is object A and object B. Okay, so this is like it states here, the mass of the object, and the V is the velocity of the object. I hope that all of this makes sense, and it's doing some good revision for you guys. So now we move on to elastic and inelastic collisions. So it says here, although momentum is always conserved during collision, kinetic energy may not always be conserved. If the total kinetic energy of the system before collision is equal to the total kinetic energy of the system after collision, then the collision is said to be elastic. Okay. So you guys see that. It means here, if the EK before or EK1 is equals to EK1 is equals to EK2. Let me just show you guys. Okay. Okay, so it means that these two parts, remember, it's 1 and 2, it's product A and product B, and this is product A and product B. These are the initial ones and the final ones. So if these two, okay, if these two are equal to, if you calculate them like this, and you have P initial is equals to P final, and you add them together, and they both become equal, it means that we have ourselves a elastic system. So that's what it means. That's how you can calculate. Whenever they ask you a question, is this an elastic or inelastic system, you're going to do that. You're going to find the answer to P total before collision plus P total after collision. If the answers are the same, they are equal. If the answers are not the same, then it means that they are inelastic. Okay. So, however, if the total kinetic energy before and after the collision is not the same, then the collision is said to be inelastic. So make sure, grade 12, that you understand how to know what is elastic, how if the system is elastic or inelastic. This is very important because it always gets asked in your question papers, and you need to always make sure that you have it. Okay. So it says the kinetic energy is often transferred to sound, light, and internal heat due to friction. Okay, so friction always has an opposite direction to the applied force. Always remember that. And in this case, kinetic energy is transferred to sound, light, and internal heat. So now we come to a collision example. Okay. So it says a ball of the mass 100 gram is moving at 10 meters per second to the right when it collides with another ball of the mass of the 150 gram moving at 10 meters per second to the left. So after the collision, the 100 gram ball moved with a velocity of 7 meters per second to the left. So what they want to know is, please, number one, calculate the velocity of the 150 gram ball after the collision. And number two, is this collision elastic or inelastic? Those are the two big questions that we're trying to solve here. So what do we know? What do we have? First of all, I asked you guys, make sure that you draw the diagram so that you know what you're talking about. As you can see here, the diagram is drawn. We've got our 100 grams and our 150 grams to show that they're both moving at the same speed towards each other. But after that, this one is moving at 7. We do not have the speed of the second one. So what are we going to do? This is also a sign you can use to show the total or the net momentum, the net initial momentum, and the net final momentum. Okay, so it's going to be M1 V1 plus M2 VI2. So we first start with this initial side. This is our initial side. So basically this is initial, this is final, and this is where our equal sign lies. So the mass is the same for both of them. So it will be 100 times V1, which is what is given here, and plus mass 2, which is 150 times the initial one. So now we have sorted out the initial value. So now we need to sort out the final momentum. It's going to be M1 VF1 plus M2 VF2. So we have it right here. What we know is definitely constant or is the same is the masses. So this mass here is still 100 gram and this one is still 150 gram. Okay. So now you've drawn everything. And please, guys, do not forget to change into the SI unit. As you can see, this is in meters per second. It's good. But our gram, our mass is in gram instead of kilogram. And we know that in momentum, we work with kilogram and kilogram alone. So this will be 0.1 gram and this will be 1.5 gram, 0.15 gram. So guys, please make sure that you always change, because If you do not change it to the SI unit, then your answers is going to be wrong. So if you want your correct answers, make sure that you have it in the correct SI unit. Okay. And also, we need to choose which direction is going to be positive. In this case, they've chosen this right to be a positive. So which means this one is a negative. Very important that you guys never forget to choose a direction, because if you don't choose a direction, you're going to end up writing 10 here and writing 10 here without changing the sign. And once again, everything is going to be wrong. So please, grade 12, make sure that you put your correct signs and you've chosen a certain side to be a positive. And remember, guys, you don't just say now this is positive and now this one is positive, but it's moving in an opposite direction. It means that if this is positive, then if your right side is positive, if this one is moving to your left, then it will be a negative. Okay, so we're going to substitute everything, but you can see here what we have left is our final velocity for our second object, because it's what is not given here. There should be a question mark here that shows that there is nothing here. So we are looking for this mass. And also, while we add it, because velocity is a vector, we will know the direction. Okay. So using this as reference, we will know the direction. So if like here we said, take the right as positive. If your answer is going to be positive, then we're going to say to the right. But if your answer is negative, then it means that we're going to say to your left. Please always bear in mind of those kind of tricks. Okay, then when we put it together, we're going to take everything to this side. From here, it's going to be minus 0.7, or it's going to be plus 0.7, and that will be equals to 15 divided by VF. And you take the sum of all of this and you divide it by 15, and that's going to give us 1.33 meters per second. And because it's positive, it's going to be to your right. Okay. And then they wanted to find out if this collision process is elastic or inelastic. And remember what we said, guys, we're going to calculate the total final final momentum for these two, and the total final momentum of these two, and the initial and the final. So we're going to equate them to each other. If they're equal, it's going to be elastic. If they are not equal, then it's inelastic. So now we're going to start. Here is the sum of EK initial. Okay, remember here we said you always, it's the definition of elastic or inelastic is we use the kinetic energy. You don't use momentum anymore. To prove the elasticity, we use the kinetic. So it's the sum of the initial kinetic energy is going to be half mv squared plus half m2v squared, and that should give you an answer, right? And then we go to the kinetic energy for our final momentums, right? And that is going to give us 2.58. So which means that this is going to be an inelastic system. Why is that? Because these two are not equal, you see. So that's the reason. The sum of EK initial is not equal to the sum of EK final, and that's why we got a inelastic system. So now we're moving to impulse. What is impulse, guys? Impulse is defined as the product of the net force acting on an object and the contact time that the force acts. Okay. So also F net is equals to F net times time is equals to the change in momentum. Okay. So basically, this is how we define impulse. When you write impulse, impulse is equals to F triangle T, newtons per second, F triangle T. So that's how you get your impulse. And your impulse is equal to your change in momentum. Do you guys see that? But the only difference that the SI unit is not the same once again, but it means that. So for the F triangle T, so basically this symbol right here is what represents the change in momentum. So our F triangle T is the impulse measured in newtons per second. Then we've got our net force, which is measured in newtons. And we've got our change in time, which is measured in seconds. And change in momentum is measured in kilograms meters per second. Okay. Okay, just too quick. So now it says here, consider the tennis ball in example 1. If the tennis ball is in contact with the wall for 0.1 second, what is the impulse of the wall on the ball? Okay, so we've got your tennis ball, it gets into contact with the wall at 0.1 second. What is the impulse on the wall? So our change in, because we're still considering what we did in example 1. Ooh, I've just moved a bit too quick. Yeah. So here we had already found our change in P. So our F triangle T, F net triangle T is going to be equals to your change in momentum. And your change in momentum was given as 4.76. So which means that it's going to be 4.76 newtons per second to the left. Okay. So impulse and impulse is equals to the change in momentum, but for each case, the standard units are the same. Okay. So for momentum, we're going to use meters per, kilogram meters per second. Sorry, there's a K missing it. Kilogram meters per second. But for F triangle T, we use newtons per second. So number 2, it says calculate the force exerted by the wall on the tennis ball. Remember what we mentioned, guys, that for the velocity of an object to change, there needs to be a force that is applied on that object. So when you throw a ball on a wall, whether it bounces back or it falls down, there is some force that is applied, be it 0 or be it 0.1, but there is a force that is applied. So the solution in this case, we are looking for the force. We've got our change in time, which is 6 seconds, and we've got our change in momentum, and that's going to be 4.76. So the F net is equals to 47.6 newtons to the left. Okay. Why is it left? Because the answer is positive, and we've chosen left as positive. So if the ball experiences a force of 47.6 newton to the left, then the wall should experience a force of 47.6 to the right due to the tennis ball. So this is according to the Newton's Newton's third law. Both objects experience the same size force, but in opposite direction. So basically, this is also a collision theory because they experience the same force, but their force is in opposite directions. Okay. So now I'd like us to go and do some few problems from our question papers just to see how you guys need to answer them. So this was taken from the NCS November paper 2012. It says here, the diagram below shows a car of a mass m traveling at a velocity of 20 meters per second. So here's our first car. It's traveling at 20 meters per second. East on the straight level road. So there is no friction from the ground, for example, humps, etc. So it's traveling on a smooth road, and a truck of a mass of 2 meters traveling at 20 meters per second. So just by looking at these two, this one is a large truck and this one is a small car. They're both traveling at the same speed, but which one would stop first? It would be this one because even in the body, it's not so big, okay? So ignore the effects of friction. So when we ignore that, remember we also spoke about it, that it's in an isolated system. So it says the vehicle collides head-on. So this is a head-on collide. So when they get here, pooh, they bump each other and they sort of stop, okay? And stick together during the collision. So they do not collide and separate like particles. In this case, they bumped each other and the car stopped. So which means that their final velocity for both cars is going to be a 0 because there is no movement after the collision. So now they want to know, number 1.1, they want you to state the principle of conservation of linear momentum in words. So this is going to count for you for 2 marks. They want you to state the principle of conservation of linear momentum. And what do we know about that? Is that the total linear momentum remains constant. So the part where you say remains constant, that's where you get your first mark. And in an isolated system, and that's your second mark. So this question is out of 2 marks, okay? So remember, always mention your isolated system. Why we spoke about isolated system? Because we are excluding all external factors or external environmental conditions into this problem. We're just focusing on the 2 cars that have bumped each other at a constant speed of 20 meters per second. So on 1.2, it says, calculate the velocity of the truck or car, the truck car system immediately after collision, okay? So now they want the velocity of the truck car system, because now, remember they collided and they stuck together during the collision. But we do not know that after they stuck together, which direction they moved in and on what speed, okay? Because when they hit each other, they're not going to stay stationary. There's going to be some sort of movement, which is likely this car over here is going to be, this car is going to take the direction of this big truck because this truck is much more heavier. So it takes precedence on this system. So once they join together, it's going to bump each other and they're going to move onto your left. You see, guys, what I'm trying to make you guys see. Sometimes you just need to have a practical scenario where you guys yourselves try and see that how would it work when you look at the practical means against the theoretical means as we have worked throughout this problem, okay? So let's see how they calculated it. So they calculate the velocity of the truck car system, okay? So what do we know here? We know that Pi is equals to, P initial is equals to P velocity, okay? Or we can say that the conservation of momentum is that both of them are equals to each other, okay? The sum of the momentum, basically this is the resultant momentum. The sum of the total momentum of the one object is equals to the sum of the momentum of the second object, okay? So in this case, this one here, this sum here is going to be the small car and this one is going to be the truck, okay? So now we're going to have it. What we're going to do is we're going to split them apart, right? And we're going to put the initial ones, which is this one here, on one side and the final velocity on one side. We know that the final velocity is going to be the same for both of them because now they are stuck together and they are moving at the same velocity. So we can have our VF. But look at the mark allocation. You're going to get the mark for stating the Newton's law right there. Okay? You're going to get a mark for that. And then you separating them, you're not going to get marks for that. What's most important is going to be your substitution. What is the substitution that you're using? The mass in this case is not going to be most important because they told us that 2m and the other one is mass. So you just write it the way it is. You write your m and your 2m. So which means that the truck is twice the mass of the car, right? So when you substitute everything together, you are going to have the m's together, right? So you can even divide the m's together, but after you have substituted, you see, guys, look at how many marks are there. You got a mark for substituting, for writing the correct equation. Then you had a mark for your individual substitution. That this one is the first car, this one is the second car, and this is the two cars that are stuck together. Okay? So now you're going to divide everything by m, or you can divide it later. It does not matter. But now you can add them. It can be minus 40, and this will be 20, and this will be m plus 2m. It's going to give us 3m. So minus 20m divided by 3m is going to give us our final velocity. And our final velocity in this case is going to be a negative answer, and it's going to be minus 6.67. And remember what we chose. We chose east as positive. Okay? Always make sure you choose a direction. So if east is positive and this is a minus, it means that it's going to be 6.67 meters per second to your west. You see how many marks you get just for rewriting your answer according to your SI unit and according to direction. Remember, guys, when you work with vector units, you always have your direction, and this is going to give you 2 marks. So imagine how much marks you would have lost if you just stopped on final velocity is equals to minus 6.67. It's never the final answer. The final answer is 6.67 meters per second minus 1 to your west, and there you will have your total 6 marks. Okay, I hope we're all good. So on 1.3 it says, on impact, the car exerts a force of magnitude F on the truck and experiences an acceleration of magnitude A. So 1.3.1 says, determine in terms of F the magnitude of the force that the truck exerts on the car on impact. Okay? So what are we going to do now? Now we're going to go and say F triangle T is equals to M times A, right? Remember we spoke about as an example like this beforehand. 1.3.1. So they say here, determine in terms of F the magnitude of the force that the truck exerts on the car on impact and give a reason for it. Okay, so on impact, the car exerts force magnitude F on the truck and experiences an acceleration of magnitude A. So determine in terms of F the magnitude of the force that the truck exerts on the car on impact. So that is going to be F, and it's going to be our Newton's third law. Okay, so that's going to be your 2 marks. So 1.3.2, it says determine in terms of A the acceleration that the truck experiences on impact. Okay, so first we wanted to know the force that truck exerts on the car on impact, and now in terms of A, the acceleration that the truck experiences on impact, and give a reason for that. That's going to be half of A. Okay, and why is that? Because the truck experiences the same net force but has twice the mass. Remember, we said M is against 2M. Okay, so since A is since acceleration is indirectly proportional to the mass, then the acceleration must be halved, okay? Because if this acceleration is 2 and we have 2 over there, it's going to be a half a, okay? So on our third problem, what they ask there is both drivers are wearing identical seat belts, okay? Which driver is likely to be more severely injured on impact? And explain your answer by referring to the acceleration and velocity. Just looking at these two cars, they're both traveling at the same speed, but this one is much larger, okay? So which means that it's got a much more force than this smaller car, okay? So in as much as they're traveling at the same speed, but their mass is not the same. But because this mass is twice the mass of this small car, then it means that this small car is the one that's going to be severely damaged because it's much smaller than the truck, okay? So it says here, the car driver. Okay. Okay, so here it says the car driver. The car driver has a greater acceleration due to the smaller mass, but the same net force. So therefore, the car experiences a greater change in velocity. Okay. So do you guys see where all the marks are? The first one is explaining what is asked, and you get 2 marks for explaining how you got that answer, or by motivating your answer. Okay. So because here they said in terms of acceleration, they said the car has a greater acceleration. So that's 1 mark there. And therefore the car experiences a greater change in velocity. Okay. I hope that all of that makes sense. So now we're moving on. So let's go to the next problem. This is question 2, but you guys see what's happening. They sometimes ask the same questions in different ways. You must note that all the time, that sometimes they'll ask you a similar question, but change the values or change what is required from that question. So this was taken from 2011. I'm just trying to show you that, consecutively, you might get questions that are the same or similar, but are not the same, okay? Because sometimes you find that you do a question paper, let's say you do a previous paper, and then when you meet a certain problem like that in the exam, you think that it's the same problem, and you start writing those answers according to what you found in those answers that you saw on your book. So you need to be careful. For example, with this problem here, you can see that here for the car it was 40 meters per second, but for the truck now it's 20 meters per second. So now the velocities are not the same like it was on this problem here. You see, here they were both equal, but the masses were different. So guys, please, you need to have a sharp eye. You need to read and you need to understand all the problems that you're working with, not just know what answers you're going to get from them. So it says here, a patrol car is moving on a straight horizontal road at a velocity of 10 meters per second east. At the same time, a thief in a car ahead of him is driving at a velocity of 40 meters per second in the same direction. So while traveling at 40 meters per second, the thief's car of mass 1,000 kilograms collides head-on with a truck of a mass of 5,000 kilograms moving at 20 meters per second. After the collision, the car and the truck move together. So basically what this means is that the collision is going to take place and both the objects are going to stick together and move in one direction. Okay, so which means our final velocity in this case is going to be the same. So we ignore the effect of friction. So we just assume we are on a straight row. Okay. So here, once again, they want you to state the law of conservation of linear momentum in words. And that's only for 2 marks, but it's a lot of marks when you are writing an exam. So it says here, the total linear momentum remains constant in an isolated system. So you see the mark allocation. We still have it remains constant, and we still have it on an isolated system. So on number 2, it says, calculate the velocity of the thief's car immediately after collision. So how are we going to do that? Immediately after collision. So we're going to do basically the one side. We need to choose a side. Which one is positive? Is the right positive or is the left positive? In this case, we chose the right as positive, which is the direction in which the car was moving on. Okay. So we're going to say, you see here, we're gonna say initial momentum of both cars is equals to the final momentum of both cars. But here you see what's happening here. The VF is going to be only one because now they are stuck together and they are moving in one direction. But initially, they both were moving on the same direction. So what are we looking for? We're looking for this final velocity. So you're going to substitute accordingly, guys. And remember, accordingly, I mean that as grade 12, you should be able to get your signs right. You need to know, don't forget the signs, guys. It's always important to choose your positive direction, whether it's up or down, whether it's left or right, east or west. Always choose your positive direction, because here we are working with a linear systems. Okay, so you either have left or right, up or down. You're not going to have 3-dimensional systems like you will in the future, but this one is one direction. So you need to know which direction you're going to choose. So here, and remember I told you guys, you're going to get marks for all your individual calculations. So if you substitute your mass plus the initial velocity of the car, you're going to get a mark for that, because you also have your positive direction indicated there in your equation. And for the truck, it's going to be 5,000, and the minus, okay, it's going to show, you need to have your minus there, and that will all be equals to the sum of your masses, because remember now they are stuck together, but we're looking for the velocity. So it's going to be minus 60,000 is equals to 6,000 final velocity. And what we're looking for is the final velocity, and that's going to be minus 10. So what does this minus tell us, guys? You see, in the sometimes you also get a mark for writing this part. So minus 10 tells us that because right is positive, it means that left is negative. So it's going to be 10 meters per second to your left. So do you guys now understand slowly why it's very important to choose a direction, and how it will still give you the same answer according to the information that was given? Okay. And make sure you substitute your directions right at all times. So on 2.2, it says, calculate the velocity of the thief's car immediately after collision, right? We've already found that it's going to be on that direction, because this is a huge car. Okay. So on number 2.3, it says, research has shown that forces greater than 85,000 Newton during collision may cause fatal injuries. The collisions described above last for 0.5 seconds. Okay. Forces greater than 80,000 Newton during collision may cause fatal injuries. The collision described above lasts for 0.5 seconds. Okay. So the collision, the accident, when it happened, because the small car was moving at a much faster rate, it only lasted 0.5 seconds. Determined by means of calculations whether the collision above could result in a fatal injury. So what they say here is that according to research, it shows that if a force is greater than 85,000 Newton during collision, it may be fatal. Okay, so what are we going to do? Now we're going to first start with the force on the car. Okay, why are we doing the force on the car? Because um, the car, remember here when we calculated the velocity, it showed that after the collision, they moved in the direction that the truck was moving on. So which means that the force impacted the car much more. So now the force on the car, we're going to change it to be a positive. So F net change in T, which is this case, guys, the minute they start asking about the collision and if like with respect to time, then you know that now we're talking about the change in momentum. Okay, because now we want to know the force and we are doing it in according to time. Okay, so they've given us the time. So it's going to be F net is equals to change in time is equals to change in momentum. So that will be equals to mass times final velocity, initial velocity. So you're going to make your F net the subject of the formula. So it's going to be mvf minus vi divided by change in time. And change in time has been given as 0.5. So which means that that is going to be equals to 100,000 newtons to your left, because our answer is minus and our right is what is positive. Okay, so the F net is greater than 85,000. Therefore, this collision is going to be fatal. Okay, so guys, some things you might not get them in the textbook, but just by understanding the question and describing what is happening in the question, you will be able to understand how to answer a question. For example, with this one here, you didn't have to be told, but you could see just by reading the question that this one is more than 85,000, and research has said that if it's more than 85,000, it's a fatal collision. So which means that this that we have here was a fatal collision. Okay. So now we're going to move to the next question. Okay. Oh, guys, do you guys see how all of them are almost similar? They always have some similarity, the question that they were asked with regards to momentum. You guys notice that similar but not the same. Similar but not the same. Okay, so make sure you understand the content of the question before you answer. That's why I always tell you guys to always write what is given before you attempt your question. Write what is given, write on the sketches, write on the question paper, write even on the cards, you know, just for you to understand. Do anything to understand your question. Okay. So it says here on question 3, this is taken from the 2013 prelim paper. Okay, this was the Gauteng prelim paper. So it says a delivery van having is moving towards the right at a constant velocity of 10 meters per second. The delivery van collides head-on with a car of a mass of 2,000 kilograms, moving at a velocity of 15 meters per second towards the left. Immediately after the collision, the car moves at a constant velocity of 5 meters per second towards the right. Okay, so it says here we have our delivery van, 5,000 moving towards your right and at 10 meters per second. And now you have your car, the small car at 2 kilometers. Guys, you must always remember, you guys see, we focus on different problems with different weights, but the larger object always takes the direction of the velocity. Remember, always after the collision, it always moves in the direction of the larger object. So you guys should also pay attention to that, okay? So immediately after the collision, the car moves at a constant velocity of 5 meters per second towards the right, okay? So you see, it says it moves 5 meters per second towards your right, okay? So what do they want to know here? What they want to know here is for us to calculate the magnitude of the velocity of the delivery van immediately after collision. So which means that in this case, our cars didn't stick together and they are not moving on the same direction. So which means it was just a collision and they both probably moved in different directions, because as you can see here, the car was moving towards the left, but now it's moving towards the right. So which means this was a collision whereby each car took its different direction. Okay. So now they want to know the magnitude and velocity of the delivery van. So now we're going to have a different approach to our equation. Remember before we had one final velocity, but now it's not going to be the same anymore. We're going to have individual final velocities. We're going to have the final velocity of the van, and we're going to have the final velocity of the car. Okay, now we're going to separate them because they are not the same. So make sure you got that right. Do not, cram your answers. Make sure you understand your answers. Okay, so now we're going to have our total momentum before is equals to total momentum after. So we got both of them this side for the initial ones for math 1 and math 2, and we got the ones for the final. Remember, see, like I told you, you're not going to say M1 plus M2 equals to VF because they have split. They didn't stick together like we've done with other problems. Okay, so from there on, we substitute what we have. And don't forget, guys, in all problems, you need to choose your direction. Which direction of yours is positive? In this case, they chose right as positive, but you can also choose left as positive. It will still give you the answer. We're going to do them both. You see, we've got right here and we've got left here. Okay. So when we substituted, we're going to make VF1 the subject of the formula, and it's going to be a positive answer, which means that it's going to be 2 meters per second to the right. This answer is not complete. It needs to say 2 meters per second to the right. Okay. And then if we had chosen left as positive, you see what would that change? It would change this sign here, and it would change this sign here. Okay. And then in this case, it would still give us 2 meters per second, -1 to the left. Okay. I hope that all of this is sinking in well for you guys and you slowly understanding. We still have some more question papers that we're going to be working through. So if there's any way where you get stuck, you should just holler black and we can go through it. So now we move on to this one. It says on number 3.2, calculate the change in kinetic energy of the system. Calculate the change in kinetic energy of the whole system. Okay. So basically, it means that we're going to have the change in potential, change in kinetic energy of the van is equals to the change in kinetic energy of the truck. Okay. So this is what we're going to have right here. Because this is a minus, we're going to once again put our final ones together. We're going to group them again. Okay. We're going to group them according to like. Okay. So this is the total kinetic energy after minus the total kinetic energy before. Okay. So we're still on the law of conservation of energy in this case. We're still going to go on revision on more problems on our work energy and power with kinetic energy. But in this case, you need to know it as well. So this is your change in kinetic energy, the total kinetic energy after minus the total kinetic energy before. So the total is going to be the sum of the two, right? But do not forget your signs, guys. Whatever you've made positive, make sure that you will make a positive here as well, okay? Make sure, do not forget that part. As you can see here, this is going to be positive because let's go back. Remember this one. This was a truck. The truck was 10 meters per second, right? So the truck and these two, oh yeah, according to the answers that we received, 15. Yes, here's our 15 meters per second. So this one was going on this direction, and but when it came back for the initial one, this one was going on that direction, and this one is going on the opposing direction. This is 15 meters per second, right? But when we got to the after the impact, this one was going on the opposite direction, and this one as well. Okay, so that's why we have one negative there. So this one is the 5,000 because here it's the before, right? So before you have your 10 meters per second because it's this car that's going this way. Remember, we chose right side as a positive, and then minus 15. In this case, our 15 is a negative. And see here, we chose right as positive. And that will be equals to, we're looking for the final velocity. But we know that with the car, the final velocity of the car is going to be positive because they mentioned it in the problem that when it gets after collision, it moves 5 meters per second to your right. So that's why it's positive here. So we're looking for our final velocity for the truck. So what does that mean? That's going to give us 2 meters per second. So it's going to be 2 meters per second to the right. Don't forget, this one is an error here. It needs to say 2 meters per second to the right. That's your final answer. Okay, it's not just 2 meters per second. What's your direction? We're working with a vector. A velocity is a vector. Do not forget that, guys, please. Okay, so we can also do it the other way around, where we have left as positive. Even if we have left as positive, if left is positive and we get a negative answer, it means that now it's moving to the right again. Okay, and right is the right answer. So it's going to be 2 meters per second to the right. Okay, and here you must make sure that whatever direction you choose, you substitute the correct. I think, guys, you know, grade 12 papers, most people get wrong answers on momentum because of the direction that they've chosen. Some people, they cannot you know, substitute properly with the direction that they've chosen in their problem, and that's why they lose a lot of marks, especially when it comes to momentum, because you can know the equation, you can know the values you need to substitute, but if you do not know the direction and the sign that you have to use for your direction, then your answer is going to be completely wrong. So guys, please bear that in mind. It's very important. Okay, so now we get to one of my favorite questions. It says, what type of a collision is this? Right only, elastic, or inelastic? It's not so easy, right? Because we have to prove that. Okay, so it's going to be inelastic. But okay, let me just go back. Okay, what type of collision is this? Is it elastic or inelastic? Remember what we spoke about, guys? We said that if the total kinetic energy of the car before is equals to the total kinetic energy of the car after, I mean the combination. If you have the initial kinetic energies is equals to the final kinetic energies. If those two are equal, then it's going to be an elastic. But if they are not equal, then it's going to be inelastic. But why, guys? Why do we get an equal? Why do we usually get an equal amount? We get an equal answer because they stick together. Okay, so that's why our initial kinetic energy is equals to our final kinetic energy. In this case, however, it's not sticking to, they do not stick together. Each one goes its separate way, and that means that our kinetic energy is not going to be conserved, it's not going to be equal. Our initial kinetic energy is not going to be equals to our final kinetic energy, and therefore this will be an inelastic system. Okay, I mean inelastic collision. Okay, so other things you guys need to know, sometimes they'll ask you to prove it, but if you are not sure, guys, even though it's 1 mark, if you are not sure of the answer, just do a quick calculation of the change in kinetic energies just for yourself so that you can have a correct answer, because 1 mark Goes a long way in physical sciences. Okay. So now we're moving on to 3.4. Number 3.4 says if the collisions lasts for 0.4 seconds, calculate the magnitude of the force that the delivery can exert on the car. What does this mean, guys? What do we know about momentum with respect to time? We know immediately that once they put time in momentum, then now we are talking about impulse, okay? So which means that now we are working on impulse. So what they want us to calculate, they want us to break down, and remember impulse doesn't have a sign. Impulse is equals to F triangle T. So what are they looking for? They're looking for the F net. So the F net is what we're looking for. So with F net triangle T is equals to the change in momentum. Okay. So let's see how we calculate this one. Okay. So there we have it. We're going to have F net is equals to change in P is divided by change in T. So here the substitute the T underneath here, and that will be equals to mass of car 1 times velocity of final 1 minus mass 1 times velocity initial velocity 1. Okay. So here we've chosen the right as positive. Always, guys, whatever calculation that you have to do when it comes to momentum, the first step that you take is choose a direction. You might not get a mark for your direction, but you'll definitely lose a mark for not substituting the correct direction. Like here, as you guys can see here, this mark actually came from this direction that was written here. Okay. Yes, because here they're looking for the delivery van. Okay, so it's this one right here that we are looking for. Okay, so we're looking for the force that sits on the car. So that's why we're using M1. The change in mass, the change in momentum is M1 F1 minus M1 VI. Okay, final minus initial and divided by the change in time, which was given to us already, and that is going to be a 0.4, and our answer becomes 100 Newton. So I just want to show you guys, like I mentioned before, it doesn't matter what you choose as positive. If left is positive or right is positive, it still should give you the same answer as long as you have stated left is positive, and here you've got your minus 100, but you're going to change and say 100 newtons to your right, and here 100 newtons to your right because it's positive. Okay. So there's also another way that you could have done it. So for those people that love calculations that have to do with forces, but I don't think this one is necessary because I'd like us to stick to the equations that we've been working on throughout our revision questions. Okay. So now we're going to another problem. I think this is a problem from, let me see. I think this is a problem from 2018. It's also an exam question, guys. 2018 on the May exam, okay? So it says here, a bullet moves east at a velocity of 480 meters per second. So this is a new thing that we have been using. But remember, we've worked on a case like this where your object is continuing at a different rate, okay? At a different speed. When the speed changes or it slows down, okay? So it says a bullet moves east at a velocity of 480 meters per second. It hits a wooden block that is fixed to the floor, okay? So this is a wooden block, and it gets hit by this bullet. So somebody's shooting, probably training how to shoot, okay? So the bullet takes 0.1 second to move through the stationary block and emerges from the block at a velocity of 80 meters per second east. Okay, so obviously if it's shooting, it's going to hit the block and the speed is going to be slowed down because of this obstacle that is there between the bullet and its final destination. Okay, so they say once again, it's in an isolated system. So they can either state it as isolated system, or they can say ignore the effect of air resistance. So if they say you ignore that, it means that you're only going to focus on your on your net force as your applied force, and you're not going to have to calculate your force of friction, etc. Okay. So now they want to know, explain what is meant by an isolated system as it's used in physics. Okay. Okay. Oh, these answers here, I have them actually. Mm, okay, I'm just looking for. Mm, I'm just looking for our problem at hand. Mm, okay, so sorry for the slow network. Oh, yeah, here we have it. Okay. So in number 4, they want to know, they want us to explain what is an isolated system in physical sciences. So it says here, isolated system is a system on which the resultant or net external force is zero. Okay. So you get 2 marks for stating that it's a system where the resultant external force is zero. And remember, from the diagram that I showed you guys, before. Oh, but it's a bit far. I don't know if I'll get you. Yes, here we have it. Mm, yo. Okay. So basically, what they mean about isolated system, remember we spoke about it. It's a system whereby we ignore. Oh, it's moving so fast. I think I'm just gonna let it go. Yes, here we have it. Remember, we spoke about an isolated system whereby we ignore all the environmental effects or environmental impact or air resistances, all of that. So an isolated system is the one where the external forces are equals to zero, which means that even though they are there, we do not consider them for this calculation. So basically, that's what it means in that problem where they ask you to calculate, to explain what it means when they talk about an isolated system. It's where all the resultant external forces is equals to zero. Okay. Okay. And then moving to the next one, it says the magnitude of the momentum of the bullet before it enters the block is 24 kilograms meters per second. So now they've given us the magnitude of momentum before, okay? So which means that now, even though we had to look for something, it's going to be much simpler because the change in momentum is equals to um, the momentum before minus the momentum after minus the momentum before. So what they want now, they want us to calculate the mass of the bullet, okay? Which is not going to be so difficult because we're just going to substitute um, what we have. I think that we're not going to go through too many options. Like they like giving us a lot of options to choose from for your answer. So we're just going to choose one that the two simple options, okay? But I like choosing basically the ones of the stuff that you've already been working with, okay? So I think we'll choose the first option here, okay? So the first option says the net force times time, which is basically impulse. This is our sign for impulse. This is our SI. I mean, when you write impulse, this is what you write. You don't write I, because I stands for something else. You write F net triangle T is equals to the change in momentum. So F triangle T is equals to the momentum of the bullet, the final momentum of the bullet minus the initial momentum of the bullet. Okay. And what we're going to have here, we're looking for okay, I think I'm too forward, guys. Oh, here we are. We're looking for the mass. So for the mass, we're just going to substitute what we have because we're only working with one object. It's not like the other one where we had two objects. Here we're only working with one object. So P is equals to M times V. And we're going to substitute the 24, which was given. Remember, they mentioned that the initial momentum is 24 kilogram meters per second. And that equals to the mass times the velocity of 480. So our mass is going to be this one. And remember, now this is the mass that we're going to use for all of it. So what you're going to get marks for is basically writing the equation, substituting, and getting the answer. Okay. And then for number 4.2, let's go to that problem quickly and see what they say. On 4.2.2, it says, calculate the average net force exerted by the wooden block on the bullet, okay? The average force exerted by the wooden block. So now we're working with this one right here, okay? So let's go and see how we're going to approach this one when you meet it in the exam. So it says here, for this question, this is how you're going to be marked, okay? You're going to get a mark for the appropriate formula, including the force net, because basically that's what we're going to be working with. Because the minute they put in time and the force, we know that now they've moved to impulse, okay? Number two, you're going to get 2 marks for substitution, and you're going to get a mark for the final answer, and you're going to get another mark for the correct direction. So do you guys see how many marks are there? They might give you out of 5, but you need to know where exactly you're going to get your marks from so that you don't end up writing a whole page of problems with a lot of equations only to find that you've written things where you do not get enough marks from. So it's going to be F net triangle T is equals to change in P, and then we're going to have the final momentum of the bullet minus the initial momentum of the bullet, and that is going to, now we're going to substitute because we're going to break them down, right? So we're going to have the F net times the time, which they've already told us is 0.01 seconds, and that will be equals to, now we have the mass which we have calculated there, which is 0.05 times 80, which is the final velocity of the bullet. And then we minus it with 24 because 24 is the momentum that was already given to us. And therefore, the answer that we're going to get there is going to be a minus 2,000 newtons, okay? So according to what direction you have chose as positive, in this case, we chose east as positive. So if the answer is minus, it means that it's going to be 2,000 Newton negative. If we had chosen west as positive, then it would have given us a positive answer, and we'd still have to write 2,000 Newton west. You guys notice that? Guys, really thank you guys so much. I hope that you've had a good fair share of our revision for grade 12, physical sciences, momentum and impulse. However, though, I do have a homework that I'd like you guys to go and try it at home, and we can probably do it together on our next class on Saturday before we get to what we need to do for next week. Okay. So can you please take a screenshot of these problems? And I'd like you guys to go and do this problem. We're going to start with it next week when you come to class. And thereafter, we'll continue with our list. Just go and try it out and test yourself and see if you understand this revision that we've been doing for the past 2 hours. Thank you guys so much for joining me into this class. My name is Nonkulego Madondo. I am your physical sciences grade 12 teacher. Hope you had a great lesson, and I hope that you understand everything. And please, guys, join me again next week, same time, same place. And thank you and goodbye.